So we're here at the example table, and in this video we're going to sketch the graph of the function negative log of x squared. Just to remind you, when there's no explicit base here, it's log base 10. So we're working log base 10. Let's start with something simple. Let's forget about the negative, let's forget about the square, let's just graph log of x. This is a graph that you should know. Just looks like this. Has a vertical asymptote at the y-axis, doesn't exist over on the left-hand side of the y-axis, crosses the x-axis at the point 1, 0, and I guess if we want to be fancy, we can label another point. It's probably worth labeling in this particular example, and you'll see why later on. This point here, let's say, is 10, 1. Remember, this is log base 10, so if you plug in 10, 10 to the first power is 10, so log base 10 of 10 is 1. This graph is clearly not to scale. Let's emphasize the word sketch, right? Just a sketch. We're not worrying about lots of points. The only reason I label this point is because we're going to have to do some stuff later on that'll make it useful. We want to label intercepts, asymptotes. Usually that's about it. Okay, so let's start thinking about this x squared. Whenever you're dealing with logarithms, it's always good to try to simplify your life by applying those logarithm rules whenever possible. And here we have one that we can apply because log of x squared is the same thing as 2 log absolute value of x. Why the absolute value? Well, you can't plug a negative value into a log function, but if you're squaring it, then it doesn't matter and you can. So how do we deal with these two things? Well, let's pretend that this absolute value of x is just an x. Let's pretend that for a moment. And let's graph 2 times log of x. Well, what does that look like? Well, it looks like this, right? Suspiciously like this guy. We still have something at 1, 0, but the rest just looks the same. And here's why I label this point 10, 1. It's worth noting now we've changed our scale, but we never labeled this the y-axis. So when we multiply by 2, that just stretches the y-axis out by a factor of 2 up in the positive direction and down in the negative direction. So it's going to, in theory, stretch our graph, but since this is just a sketch, we don't even have a scale. So this point just becomes 10, 2. All right, no longer 10, 1, but 10, 2. And again, notice, not the scale. Doesn't matter, just the sketch. What does this absolute value thing do, though? If we can plug in negative values, if we plug in negative 1, it behaves as if it were 1. If we plug in negative 10, it behaves as if it were 10. So that means that we can take this side of the graph and flip it. So we get something that looks like this on the other side. You get a mirror image. So this point here is now negative 1, 0, and we get another point up here, negative 10, 2. Only one last thing to do, and that's throw in the negative sign. Let's do that on a clean sheet of paper. So let's just sketch where we left off. We had a graph that looked something like this. Right? We had 1, 0 here on the right-hand side, and then something, what was it, 10, 2. And then the mirror image on the left-hand side, negative 1, 0, and negative 10, 2. Now we want to graph negative 2 log of absolute value of x. So this was just 2 log absolute value of x. Now we want to multiply the whole thing by negative 2. When we multiply the output of a function by negative 2, that's just going to take positive values on the y-axis and flip them to make them negative. It's going to take negative values and flip them to make them positive. So this negative on the outside flips the entire graph about the x-axis, right? So what we end up with is a graph that looks something like this. So we've got these two pieces. They're now flipped about the x-axis. These 2 points remain the same. We've got 1, 0 and -1, 0. And let's just label these other guys. We now have 10, -2, and -10, -2. And that's our sketch.